The United States Geological Survey has assigned a number to an unfolding geologic threat aimed at a major American city. A 1 in 15 chance of catastrophe within the next 30 years. Not a city-leveling earthquake, not a sky-darkening supereruption, a flow of volcanic mud, a slurry of rock, ice, and debris the consistency of wet concrete, descending a mountain at over 50 miles per hour. As of the latest weekly update on July 3, 2026, the volcano is at a normal green alert level. Standard background seismicity. Quiet, right now, thousands of people are skiing on its 12 named glaciers. They are dining inside Timberline Lodge, a national historic landmark built at an elevation of 6,000 feet. They are sleeping in the villages at Mount Hood, communities built directly on top of the hardened debris from prehistoric volcanic mudflows. They are standing on ground that has moved before and will move again. But the most dangerous part of this story is not the eruption that could tear through these communities. It is the collapse that could happen with absolutely no warning at all. The part of the mountain that could simply let go, silently, under nothing more than the force of its own considerable weight. To understand what is happening 50 miles east of Portland, Oregon, you have to understand the mountain itself. Mount Hood is not Mount St. Helens. Popular imagination pictures a volcanic eruption as a singular, violent explosion. A Plinian column blasting ash tens of thousands of feet into the stratosphere. Mount Hood is different. It is more insidious. It is a dome-building stratovolcano. For the last 500,000 years, it has not violently cleared its throat. Instead, it slowly, patiently extrudes thick, viscous lava, andesite and dacite magma that is too thick to flow far. It piles up at the summit, cooling into massive, steep, and profoundly unstable domes of rock. The current one, a prominent feature on the upper southwest flank, is called crater rock. It is what's left of the last major eruptive phase, a period that ended around 1793. And for over 2 centuries, crater rock has been sitting there, venting sulfurous gases. It is a constant, visible reminder that the volcano is active. But the real threat is invisible. It's happening inside the mountain. The heat and acidic gas rising from the magma chamber below are chemically rotting the mountain's structural core from the inside out. For decades, this process, called hydrothermal alteration, has been relentlessly transforming solid andesite rock into weak, unstable clay. It's a slow-motion degenerative disease. The skeleton of the mountain is being digested. This creates a severe, unpredictable risk of a spontaneous flank collapse. An entire section of the summit could simply shear off, unprompted by any new magma, offering zero seismic warning. No earthquake swarm. No ground deformation. Just gravity finally winning its long war against compromised rock. And that is where the glaciers come in. 12 of them, sitting directly below these unstable domes, holding millions of gallons of frozen water. When a dome collapses, whether from an eruption or from its own internal weakness, it generates a pyroclastic flow, an avalanche of rock superheated to more than 1,500 degrees Fahrenheit. The moment this flow hits a glacier, the ice flash melts. It doesn't just thaw, it vaporizes, mixing instantly with the avalanche of hot rock, ash, and any trees or soil in its path. This creates a lahar, a volcanic mudflow. It is not water. It is a moving mass with the density of concrete, carrying boulders the size of houses, traveling down pre-carved channels at highway speed. For Mount Hood, that primary channel is the Sandy River, a drainage that acts as a direct chute from the summit to the Columbia River, passing directly through the eastern suburbs of the Portland metropolitan area. Troutdale, Gresham. This is the 1 in 15 hazard. Not a possibility. A probability. The highest near-term lahar probability of any volcano in the Cascade Range. Zoom out, and the history written on the landscape makes the mechanism terrifyingly clear. The mountain has done this before. Repeatedly, about 1,500 years ago, during what geologists call the Timberline eruptive period, a massive debris avalanche occurred. It was an enormous flank collapse, very similar to the one scientists worry about today. That collapse generated a lahar so immense it traveled the entire length of the Zigzag and Sandy rivers, all the way to their confluence with the Columbia River. The ground on which Timberline Lodge was built in the 1930s is not ancient, solid bedrock. It is a massive, 1,500-year-old debris fan. The hotel, an icon of the Pacific Northwest, is quite literally founded on the evidence of the very disaster that could one day erase the communities below it. Its foundation is a graveyard from a previous catastrophe. And then there is the more recent event, the one that was witnessed, even if it wasn't understood. From about 1781 to 1793, Mount Hood entered its last major eruptive period. Geologists have named it the Old Maid eruptive period, and it was this sequence that built the crater rock lava dome we see fuming today. The eruptions sent a series of massive lahars down both the Sandy and the White Rivers. The landscape was fundamentally altered. Forests were flattened. Valleys were filled with feet of fresh volcanic sediment. The mountain coughed up its insides, and the rivers carried the debris downstream. Just over a decade later, in November of 1805, two American explorers, Meriwether Lewis and William Clark, led their expedition to the mouth of the Sandy River. They had reached the final leg of their journey to the Pacific. But they encountered something strange. A river, unlike any they had seen. It wasn't clear and flowing. It was choked with gray sediment, a slurry of ash and sand that made the riverbed treacherous and unstable. In his journal, Clark famously documented their discovery. He named it the Quicksand River. What he did not know, what he could not have known, was that he wasn't just observing an unusual river. He was standing in the direct, active aftermath of a major volcanic eruption that had concluded only 12 years prior. The quicksand under his feet was the last vestige of the Old Maid lahars, still being washed out of the highlands and into the Columbia. He was documenting, in real time, the lingering signature of the volcano's last great act. The mountain has been mostly quiet since. The most recent confirmed eruptive activity happened between 1859 and 1865, a period of minor steam explosions in tephra falls near Crater Rock, a geological sigh after the fury of the Old Maid period. And for the next century and a half, the mountain settled into the background. A postcard image, a recreational playground, a silent, snow-covered peak looming over a growing city. But the processes inside the mountain never stopped. The heat never cooled. The gases never ceased their work of acidic decomposition. This is the part that is so often missed. The silence of a volcano is not the same as its dormancy. Mount Hood is not dormant. It is resting. And the science of monitoring it has become a search for the subtle clues that precede an awakening. This work falls to the scientists at the USG's Cascades Volcano Observatory, or CVO. Men like Dr. Seth Moran, a research seismologist and the acting scientist in charge as of July 2026. He has been instrumental in expanding the network of monitoring stations on and around Mount Hood. In his own words, robust monitoring networks are a key tool for mitigating volcano hazards. Because volcanoes can awaken rapidly, in just days to weeks, and initial precursors to that awakening can be subtle, those subtle precursors are everything. They are the faint tremor of magma moving miles below the surface, the slight swelling of the ground, measurable only by GPs, a change in the temperature or chemical composition of the gases venting from crater rock. On a mountain like Hood, these signals are the only warning anyone will ever get. The Pacific Northwest Seismic Network, the PNSEN, maintains a constant watch. They detect small earthquake swarms on the mountain periodically. On June 5, 2021, a magnitude 3.9 quake and a subsequent swarm occurred about 4 kilometers south of the summit. More recently, between December 8th and 13th, 2023, USGS stations detected another notable swarm of small magnitude earthquakes. In both cases, geologists were able to quickly determine that the quakes were consistent with movement on regional faults, not the telltale signature of rising magma. The system worked. The alarms did not sound, but each swarm is a reminder. The region is tectonically active, and the mountain is wired to respond. Now, here is the detail that connects this geologic threat directly to the daily life of a million people. The Achilles heel of Portland, Oregon, the city's primary water source, is the Bull Run watershed, a protected area in the Cascade foothills northwest of Mount Hood. It provides clean drinking water to roughly 1 million residents in the metropolitan area. That water does not get to the city by magic. It is carried by a series of large critical pipelines. Those pipelines, the lifeline for a third of Oregon's population, run for miles across the landscape, and they cross directly over the distal hazard zones of the Sandy River. They are built on the very ground that would be inundated by a major lahar. A mudflow descending the Sandy River Valley would not need to reach downtown Portland to create a catastrophe. It would only need to reach those pipelines. The force of a lahar, a fast-moving wall of debris with the abrasive power of liquid sandpaper, and the impact force of a freight train, would not just damage the infrastructure, it would sever it. It would obliterate the conduits, cutting off the water supply to 1 million people in an instant. The Portland Water Bureau and the USGS have studied this exact scenario. The hazard maps are clear. The intersection of the city's water infrastructure and the volcano's primary debris path is not a matter of speculation. It is a known, mapped vulnerability. This is the work that has consumed the career of Dr. John Major, a research hydrologist who served as the scientist in charge at the CIVO from 2021 to 2026. His focus is precisely on the hydrological risks posed by volcanoes like Hood, the mechanics of lahars, the physics of catastrophic sediment displacement. The science is not about asking if it can happen. It's about modeling how it will happen. How fast will the lahar travel? How deep will the inundation be? The estimates are chilling. For the areas closest to the mountain, the proximal hazard zones, the time from a dome collapse to the arrival of a pyroclastic flow or lahar could be less than 30 minutes. There would be no time to evacuate. The only hope is advance warning. Days, weeks, but this brings us back to the mountain's silent sickness. The hydrothermal alteration, an eruption triggered by rising magma, would likely give warning signs. The subtle earthquakes Dr. Moran's teams are looking for. The ground swelling, the gas changes. A full-scale flank collapse caused by internal rot, however, might not. It could fail under its own weight, or perhaps be triggered by a large regional earthquake on a completely separate fault line. In that scenario, the 30-minute clock starts without a single volcanological precursor. The first warning would be the lahar itself, a rumbling sound from the mountain, a sudden, inexplicable surge in the Sandy River, and by then, it would be too late. The knowledge of this dual threat is driving a new wave of scientific inquiry. In the spring of 2026, the National Science Foundation's Subduction Zones and 4 Dimensions Initiative, or SZ4D, established a pilot project specifically targeting Mount Hood. The goal is to study the interplay of volcanic eruptions, crustal faults, and the dynamics of sediment, like lahars. It is a recognition, at the highest levels of Earth science, that this particular volcano presents a complex and urgent problem. This renewed focus comes on the heels of a surge in public attention, driven by widely circulated science media in April 2026, that highlighted both the lahar threat to the Bull Run water supply and the mountain's internal decay. The secret is out. The 1 in 15 probability is no longer a number buried in a technical report. It is becoming part of the public consciousness. And yet, a sense of normalcy prevails. The official designation for Mount Hood in the USG's National Volcano Early Warning System the end views, is very high threat. This places it in the same category as more infamous volcanoes, like Mount Rainier and Yellowstone. But unlike Yellowstone, which captures public imagination with tales of continent-altering super-eruptions on millennial timescales, Hood's threat is smaller, more localized, and statistically far more immediate. It is a rifle aimed at a specific target, not a shotgun blast across a continent. The danger isn't that it will end the world. The danger is that it will devastate the communities in its path and cripple the infrastructure of Oregon's largest city. The lives of those who live in the shadow of the mountain are built on a geologic paradox. The very forces that created the stunning alpine beauty also created the channels for its destruction. The fertile volcanic soils that support agriculture in the Hood River Valley are a gift from past eruptions. The steep slopes that provide world-class skiing are the product of dome-building volcanism. The entire economy of the region is inextricably linked to the volcano. To live near Mount Hood is to accept, consciously or not, a baseline of geologic risk. The question is whether that baseline is shifting. The science of hydrothermal alteration suggests it is. The rock at the summit isn't just sitting there. It is an active chemical experiment. The fumaroles at Crater Rock, where gases escape, register temperatures from 89 degrees Celsius to over 300 degrees Celsius. Hot. Acidic water and steam are percolating through every crack and fissure in the rock, turning strong crystalline andesite into soft, slick, unstable clay minerals like kaolinite and smectite. Every day, the structural integrity of the summit degrades, just a little bit more. Every day, gravity's pull becomes slightly more persuasive. The mountain is slowly, methodically preparing itself to fail. So Mount Hood did not just become a threat. It was set up to be a threat by its own fundamental geology, by the viscous nature of its magma, which builds steep, unstable domes, by the 12 glaciers clinging to its flanks, a ready supply of water waiting to be weaponized, by the river valleys that serve as perfect, pre-graded channels for destruction, and now by the 2 centuries of quiet, persistent internal decay that has weakened its core. The pieces are all in place. The system is loaded. The only unknowns are the trigger and the timing. The official reports from the USGCVO, like the one from July 3, 2026, provide a steady drumbeat of normal background seismicity, normal gas emissions, normal ground deformation, and that is both reassuring and deeply unsettling. It means that today is not the day. But it says nothing about tomorrow. It says nothing about the slow, invisible process of decay happening deep within the rock, a process that our monitoring networks are not designed to measure directly. We can see the mountain shake. We cannot see it rot. Against this backdrop, the ski lifts continue to run. Tourists continue to pose for photos at Timberline Lodge. New houses are built in the communities along the Sandy River corridor. Life continues under a threat that is simultaneously statistically probable and difficult to truly imagine. It remains a beautiful, imposing, and overwhelmingly solid-looking feature on the horizon. It looks eternal, permanent, but the story told by the geology, by the history of the Old Maid and Timberline eruptions, by the chemistry of the gases venting from Crater Rock, is a story of profound and inevitable change. The mountain is a living thing, on a timescale that is difficult for us to comprehend. And it is approaching another moment of transformation. There is one more thing the data cannot yet tell us. The probability of an eruption-generated lahar is 1 in 15 in a 30-year window. That number comes from a 1997 USGS report, Open File Report 9789, authored by scientists like W.E. Scott and T.C. Pearson. The math is based on the mountain's known eruptive history, but there is no equivalent number for the probability of a spontaneous flank collapse. There is no way to calculate the odds of a failure caused by the quiet, unmonitored process of internal decay. That remains the great, terrifying unknown. It could be a lower probability. Or it could be much, much higher. So, 3 questions hang over the summit of Mount Hood tonight. 1. Just how much of the mountain's core structure has been chemically altered into weak, structurally unsound clay? 2. Could a major regional earthquake on the Cascadia subduction zone, an event geologists know is coming, be enough to trigger a catastrophic flank collapse, even without any new volcanic activity? 3. And what does it mean that the water supply for 1 million people, the lifeblood of a modern American city, depends entirely on the integrity of a few pipes built directly in the path of one of the country's most probable volcanic hazards? Deep inside the edifice of crater rock, at temperatures hot enough to bake the very stone, sulfuric acid a quarter millennium old is still at work. It is dissolving solid lava, molecule by molecule, in the dark. It is patiently preparing the rock for a journey down the mountain that it has not yet begun. The pressure is building, the rock is weakening. And 50 miles away, a city of 1 million people sleeps, largely unaware of the silent methodical chemistry taking place at 11,240 feet,